I would like to introduce you to a shortcut method for finding chi-square where you don't even have to find the expectation matrix at all. And this shortcut method is given on, I'd like to find the page, if you would just give me a moment. On page 17. So if you look on page 17, it talks about a shortcut method to find the chi-square test statistic by the following formula, where A is just your first cell. Let me explain. Let's say you have a matrix, a 2 by 2 matrix, given by A, B, C, and D. So the total column here would be A plus B, and here the total would be C plus D, and the column total here A plus C, the column total here B plus D. Here's your 2 by 2 matrix. I would like to demonstrate the shortcut chi-square formula. So instead of finding an expectation matrix, you're simply going to this formula on page 17, chi-square, chi-naught squared, the test statistic, is equal to n, absolute value AD minus BC, minus n over 2 squared, divided by A plus B times C plus D times A plus C times B plus D. Let's talk for a minute about the denominator. You see, these are just the row and column totals. Here's A plus B, here's C plus D, here's A plus C, and here's B plus D. So these four go on the bottom in the denominator. And then on the top you've got n, which is this grand total right here is n, times AD minus BC under absolute value. So this is just this times that minus this times that, minus n over 2. This part is called the continuity correction. So most times this continuity correction, this is the Yates continuity correction. You can skip that continuity correction if you want your numbers to match what we were doing by finding the expectation matrix. And we will be skipping this n over 2 part. Just simply go plug into this and it'll give you the same chi-naught squared test statistic as before. Let's do it right now. This was our observed matrix. I had A and B, and the numbers were 5 and 80 for a total of 85, and 15 and 80 for a total of 95. And then my column totals here were 20 and 160 and 180. Let's label this properly. Insomnia and no insomnia. That's what I had before. So my n is 180. Let's plug in chi-naught squared equals 180 absolute value of AD 5 times 80 minus BC, 15 times 80. Close the absolute value. Forget the Yates continuity correction. Square this. Divided by all the row and column totals multiplied. So 20, 160, 85, and 95. And let's clean up this mess. Let's see. We have 5 times 80 minus 15 times 80. So absolute value of minus 800 is 800. Let's square that. Times by 180. I have 115,200,000 divided by 20 times 160 times 85 times 95. 2584000. My answer, 4.458. And let's call this shortcut. Let's see, does this match what I had before? So on page 3, I had the chi-square done the right way, the long way. I had 4.457. 4.458 using the shortcut method. So you see that the shortcut method without Yates correction will match what you had before using an expectation matrix. So we should talk about what is this Yates continuity correction. So that occurs on page 17. It says that the Yates continuity correction was designed to be used on 2x2 matrices when the sample size is small. So Yates, a British statistician, Frank Yates, decided to use a correction because we are actually using continuous methods instead of discrete methods, where here we actually have discrete counts. So he mentioned that if you are to use a continuous method such as chi-square, where you're actually dealing with discrete counts, there should be an applied continuity correction for that. And this, in fact, is the correction right here. The correction of subtracting a half before you square the observed minus expected values. Later on, other statisticians came around and said, well, if you use the correction, it overcorrects the chi-squared test statistic. So they decided to not use the correction. We see that the Yates correction reduces the chi-squared value right here, and that would increase the p-value. The p-value, which is the probability of being more extreme, would go up if this number went down. In any case, I don't expect you to use the correction. You can skip the continuity correction in the shortcut method, and you can skip the continuity correction in the original chi-square formula as well. So just to summarize what we've done here today, folks, we first began with the normal theory method for comparison of proportions, where you were given a 2x2 matrix. This is only good for a 2x2 situation. You were given a 2x2 matrix, and we actually created a z-test statistic here, and we ran a hypothesis test using z, and we came up with a test statistic of minus 2.11. This was on page 2 of your notes, of your class notes. We came up with a z-test statistic of minus 2.11, and we reached a conclusion based on that. Then we created a confidence interval for P1 minus P2 and reached the same conclusion using the confidence interval. Again, this was on page 2 of the class notes. On page 3 of the class notes, I show you the calculator command to do this entire procedure on the calculator. Stat test to proportion z-test. Next, I do the whole problem over using a chi-square test instead of the z-test. So here, of course, I do this by hand, and I take my observed matrix. I create my expected matrix by using the fact that each cell in the expected matrix is given by row total over grand total times column total. That's how I arrived at this expectation matrix. Here I find my chi-naught squared test statistic. And I go and I drop this test statistic into a chi-square with 1 degree of freedom. So actually a chi-square with 1 degree of freedom does not look this way. Let's fix that. The chi-square with 1 degree of freedom starts here and goes down only. And if alpha is 0.05, let's go find the critical value. For chi-square and 0.05. This 1 degree of freedom comes from the fact that r minus 1 times c minus 1 is equal to 1, because I'm dealing with a r of 2 and a c that's also equal to 2. So 1 degree of freedom and 0.05. Let's go to the chi-square. So this 0.05 and 1 degree of freedom gives me 3.84. That's my critical value. 3.84 is my critical value. And then I go and I drop this 4.45 number into this picture, and I'm here. So 4.4568 is equal to chi-naught squared, the test statistic. So I do fall in the rejection region, so I would reject H naught, which says that P1 equals P2, in favor of HA, which says that P1 is not equal to P2. That would be my conclusion for using the chi-square test, which we failed to mention